GO-LoW is a new kind of telescope that will allow us to view the sky at very long radio wavelengths. These are waves that are 15 meters to several kilometers in length. Because the waves are so long, we need a really big telescope to make detailed images of the sky. GO-LoW is therefore a constellation telescope made up of many thousands of spacecraft that work together semi-autonomously with limited input from Earth. GO-LoW will allow humans to see the universe in a new light, opening up one of the very last frontiers in the electromagnetic spectrum. With this new view, we'll learn about the magnetic fields of exoplanets in the local solar neighborhood, improve our understanding of how the early universe evolved from the Big Bang to the stars and galaxies we see today, and we'll map out the stuff between the stars and our own galaxy in unprecedented detail. The semi-autonomous constellation architecture we'll develop for GO-LoW will have applications to other science goals, from heliophysics to planetary science and beyond. This new mission paradigm has big benefits, including massive redundancy, the ability to upgrade the constellation with new tech, and reconfigurability as science goals change.
Humans have built telescopes on the ground and in space that can see the universe across nearly the entire electromagnetic spectrum. Gamma rays and X-rays, through visible light and infrared, and even to centimeter radio waves. But we've never seen the sky at the longest radio waves, longer than about 10 to 15 meters or 15 to 20 megahertz in frequency. At these long wavelengths, Earth's ionosphere doesn't allow radio waves to pass through. So the question is, why haven't we built a space telescope to explore this part of the spectrum? It's because a telescope must be many wavelengths across to provide resolution. So a telescope that observes waves tens of meters to kilometers long must be hundreds of meters to many kilometers across. GO-LoW is an array of spacecraft spanning thousands of kilometers. With GO-LoW, we'll finally be able to see the low-frequency sky in fine detail. And what will we see? Exoplanets in the solar neighborhood, blinking on and off with radio aurora from their magnetic fields, interacting with stellar winds like fireflies in the dark. These radio aurora carry important information about their planets, whether or not the planet has a magnetic field, how strong it is, how fast the planet is rotating, and even hints about what's inside each planet. Studying exoplanet radio aurora and the magnetic fields that they trace is an important piece of the habitability puzzle, and it's a key science goal for GO-LoW.
GO-LoW will first be delivered to low Earth orbit via a series of super heavy lift vehicles. From there, large transfer stages, here depicted, already used and jettisoned, will then propel GO-LoW from low Earth orbit into an interplanetary trajectory. The voyage will take about a year to travel the nearly 100 million mile distance. A large service module, representing nearly half the payload mass, is necessary to bring the whole scientific payload to its final operational orbit. Once there, the service module will execute an insertion burn and then be discarded. Onboard thrusters will then be used for deployment, no more than 1 meter per second of delta V per satellite, and station keeping, less than 2 meters per second per year per satellite. The final destination is the Earth-Sun L4, a gravitationally benign orbital configuration. The remote location, 93 million miles from Earth, means less radio frequency interference, which can otherwise threaten to overwhelm GO-LoW's sensitive measurements.
The GO-LoW constellation will have a hierarchical architecture consisting of many small listener nodes and a smaller number of larger communication and computation nodes. The listener nodes are small, relatively simple 3U CubeSats. Their size is roughly like a loaf of bread. They collect data with their vector sensor antennas, store it in memory, and periodically send it to their CCN via a radio link. CCNs are mini-fridge-sized spacecraft which collect and compress data from multiple LNs. They are equipped with laser communication terminals for sending large amounts of data back to Earth, and we expect each CCN to keep track of around 100 LNs. The CCN will keep track of the positions of the LNs in their neighborhood, collect and reduce LN data, and then transmit that reduced data back to Earth. Final correlation and imaging or other data processing will be done back on Earth where computational resources are plentiful.
In Phase 1, we focused on defining the architecture for GO-LoW and confirming technical feasibility. In Phase 2, we're now working on creating a comprehensive simulation of GO-LoW's operations, including the final science data products. There are two models at the heart of the simulation work we're doing in Phase 2. A multi-agent model of the constellation, which simulates the operations and interactions of all the GO-LoW spacecraft, and an interferometric processing model, which simulates the performance of the science instruments. In the multi-agent model, each spacecraft is represented by its own state machine and interacts with the other spacecraft via simulated communications, as well as with the space environment, for example, via orbital propagation. Once a science target is selected, for example, a survey of exoplanet auroral emissions, then the necessary constellation geometry is derived and communicated to the GO-LoW CCNs. The CCNs then instruct their corresponding listener nodes to efficiently move into the required geometry, and a simulated observing campaign begins. At the end of the observing campaign, the spacecraft's statuses, positions, and velocities are fed into the interferometric processing model, which then generates science data products that are retrieved from a simulated sky.
Interferometry relies on accurate timekeeping to phase up the radio waves that each LN measures. The spacecraft need to be able to measure the arrival of each wave peak accurately so that the waves can be added together constructively. Due to the speed of light, waves can get out of phase even with very small timing errors. Therefore, we set our time precision requirement at 4 nanoseconds. That's the travel time of 1/16th of a 20-meter wave. If the clocks on each spacecraft drift more than 4 nanoseconds relative to one another during an observation, the waves can't be aligned precisely, and GO-LoW loses sensitivity. We also need to measure the location of each spacecraft within a 1-meter measurement error. 1 meter is the distance light travels in 4 nanoseconds.
The CCNs get their positions in space via cooperative two-way ranging plus tracking information from the Earth. Then the CCNs broadcast GPS-like signals so that the listener nodes can measure their own positions relative to the CCN network. Measuring the time of arrival of one CCN's broadcast constrains the listener node to a position somewhere on a sphere around that CCN. A second CCN beacon further constrains the position to the circle that is the intersection of two spheres. Contact with the third CCN then pins the position to one of 2 points, and a fourth CCN gives the final piece of information that the listener node needs to determine its position. By using the CCNs like a GPS network away from Earth, all listener nodes can localize themselves simultaneously and report those positions to the CCNs.
So Mary told us about the importance of precise and synchronized clocks for interferometry, and Lenny discussed position determination using a GPS-like system. But what happens if our clocks are imperfect and our position estimates are inaccurate? We can use the simulation to study what happens. In this example, the position of the nodes are randomly perturbed by a small amount. This positional error propagates through the steps of the simulation to result in a distorted image. By studying what happens in cases like this, we can set realistic bounds on GO-LoW's performance. In addition to timing and position errors, we plan to explore failure modes. For example, if a CCN goes offline, how will the orphaned LNs regroup? We also plan to experiment with different constellation arrangements to optimize for different science cases while estimating the fuel consumption. Ultimately, we will scale the simulation to 100,000 nodes so that we can realistically assess the full-scale operation of GO-LoW.
We're excited to continue developing the GO-LoW concept with an expanded team in Phase 2. We are grateful to the NIAC program for continuing to support this work.